So as we said in the intro to thermodynamics, we're going to be talking about three major subjects. And the first of that is temperature. So what is temperature? Well, on a microscopic level, temperatures can be related to the thermal energy in the system, so how fast the molecules are moving. But we're going to think of it a little bit simpler case, and it'll do a pretty good job of covering what we need. And it's going to be just that it measures the hotness or coldness of a substance. And this is the hotness, coldness that when we touch something we feel. Our body is pretty good at figuring out what is hot, what is cold. The problem becomes that when we say something's hot, something's cold, our body is not a good indicator of giving us numbers. We like to be able to put numbers to this. So, as many of you guys know, we have a temperature system. So we come up with a thermometer, a device used to measure temperature, and we start looking at different points on it to try to come up with a uniform way of determining what is a temperature. So when we say something is 70 degrees Fahrenheit outside, we all have the same meaning. So how do we do this? Well, put a thermometer in there, some way to measure it, and actually how a thermometer works we won't cover until near the end of thermodynamics. But we agree on certain temperatures. For the scales that we use in most of physics, we use the MKS system, or we use the SI system. We base this off of two temperatures. One is when does water melt at normal pressures and normal pressure, and we set that to be a value. Well, in Celsius, that temperature becomes 0 degrees. That is our 0 degree mark. In Fahrenheit, because it's a different scale, we're using different measurements, that ends up being a 32 degree mark. So there's a reason why that 32 comes about historically, and it's actually kind of an interesting story, but we'll leave that up to you to go find. Well, we need another thing. So if we have one temperature, that's fine, but we need another one so we can properly put the tick marks on our thermometer. So we choose water boiling. And water boils at 100 degrees Celsius. So there are 100 evenly marked spaces between 0 degrees and 100 degrees Celsius from where water melts to where water boils at standard pressure. If we're looking at the Fahrenheit scale, 212 degrees is where water boils. And there's a reason why we'll use water boiling and water melting. They sit at that temperature when they go through this phase change. And we'll talk about that in another video as well. There's one problem that comes up with this, and the problem that we have is that this is 0 in terms of math. You know, if we try to multiply this temperature by anything, it's going to just turn into be 0. And we know that we can get lower temperatures than 0 degrees Celsius. Go up north, go to Michigan, Minnesota, Wisconsin, Alaska, and you'll find that 0 degrees is, in the middle of the winter, is a relatively warm temperature. We get much, much cooler up in those regions. So we want to use what's called an absolute scale. And an absolute scale uses a specific value. Instead of using where water melts as 0, we're going to choose the lowest possible temperature that can ever be achieved. And actually, because of how thermodynamics works, we have never been able to actually get to this point. But we were saying, you know, if this thing were to be at its absolute lowest temperature that can ever be achieved, we call that 0. We call that absolute 0. So we come up with a new temperature scale, and it's the Kelvin scale. And the Kelvin scale is nothing more than the Celsius scale, but shifted by 273.15 degrees. So 0 degrees now becomes 273.15. 100 degrees, it's 100 degrees higher, so 373.15. And this means that when we get down to 0 degrees Kelvin, we are at absolute 0. And pretty much at that point, all molecular motion stops. So the atoms stop vibrating around, and molecules just stop. So it's kind of an interesting temperature. We still keep the same division, so we still keep the 100 divisions. We just go to an absolute scale. There's two equations that you might find useful in solving physics problems. The first is that the degree in Celsius plus 273 gives you degrees in Kelvin. That's a pretty easy one. The other one, a little bit more tricky to use, is to convert from Fahrenheit to Celsius. So you take your Fahrenheit degrees minus 32 degrees, and then times it by 5/9. It's a pretty standard formula you may have seen before, and if you're having problems with this, you can always go to Wolfram Alpha or Google and just have them do the conversion for you. But it's good to have that down in case you ever are not near a computer or can't use one. Well, we said that there are different temperature scales. Celsius tends to be one we use a lot in physics. Kelvin is actually probably a preferred one to it because it is an absolute scale. Fahrenheit's the one, if you're living in the US, this is the one you're probably most familiar with, but that's not the only one. There's the Rankine system, which is like the Fahrenheit system, but an absolute scale, and then there's all these other ones. And yeah, there's a lot out there. Most of these you don't know. Historically, they're interesting how they came about for the rest of these guys. Newton actually came up with, there's one attributed to him, which is kind of fun. There are a couple good things just to kind of get your head around it, since if you're living in the US, you're probably not familiar with the Celsius scale. Body temperature falls around 37, 38 degrees, which is 98.6 in the Fahrenheit scale, or about 310 in the Kelvin scale. Another one that's interesting, room temperature is about 23 degrees in the Celsius scale, for about 73 degrees in the Fahrenheit scale. And last but not least, there's a fun little one. Minus 40 degrees Fahrenheit is minus 40 degrees Celsius. So if you're ever in that weather, it is really, really cold, but minus 40 is minus 40. It's kind of a nice little number to know.